It's okay now?
It's okay, great, thank you.
Thank you very much. Now, the talk is about the building blocks of the spiral arms in galaxies. A great proportion of galaxies are spiral galaxies in the universe, and up to 2/3 of the spiral galaxies have a bar in their center, and they're called barred spiral galaxies, like our own Milky Way, and like the one you see on the right. And the rest of the galaxies, of the spiral galaxies, have no bar, and either they have two well-defined spiral arms, and they are called grand design spiral galaxies, like the one on the left, or they have flocculent spiral arms. Okay, now there are two, as one can see by eye, the spiral structure of these two different types of galaxies have very different shapes. So nowadays, there are two different theories that prevail for each case. For the case of grand design spiral galaxy, we have the density wave theory, which says that there are ordered orbits, elliptical orbits that can support the building blocks of the spiral arms, while in the case of barred spiral galaxies, where the perturbation is much larger and no ordered orbits can be found, there is another theory, which is a more recent theory, called the manifold theory of chaotic spiral arms, and who says that in fact chaotic orbits support these building blocks. Let's begin from the grand design spiral galaxies and the density wave theory. Well, this theory can answer very well the winding problem. Many years ago, astronomers believed that the spiral arms were formed always consisted always from the same material, from the same stars, but due to differential rotation of the galaxy, these would end up by very tightly wound spiral arms. This is something that one cannot see in the real galaxies. So they have understood that there are density waves, in fact, that are made of some regions of the galactic orbits close to their apocenters. The first who pioneered this density wave theory in the 50s was Limland, with the orbital description. He named his orbits dispersion orbits, and he tried to give some density waves, but he didn't succeed in giving a very nice figure of a spiral density wave. So his theory was not widely accepted at that time, due also to the wrong belief of the epoch that spiral structure is caused by interstellar magnetic field. Then in the 60s came Lin and Su, who tried and make a very good explanation by analytical theory of the effect of collective motion via perturbative solutions. They gave the very well-known dispersion relation that relates and correlates, for example, the pattern speed of the spiral arms with the wave number and so far with the pitch angle of the spiral arms. But this relation requires more physics, as it does not take into account the amplitude of the spiral perturbation, that is how strong is the spiral arms. Then came Callan's 1973, where he popularized the precessing ellipses, the organized orbits that can form and can give, for the first time, this nice figure of a spiral density wave. And he even computed the response spiral potential out of this shape. And then came Contopoulos in 1975, which he gave analytical explanation of the forced ellipticity and analytical calculations of these periodic orbits, the number and the stability. And he gave the nomenclature for the first time with the help of the phase space. And they named these periodic orbits X1, X2, and X3. We're going to see that only one of these orbits can support the spiral structure. And from there on, many n-body simulations and self-consistent models have able to solve these precessing ellipses in 2D or 3D models. In a recent study of ours submitted in Astronomy and Astrophysics, We use a spiral galactic model in order to study these precessing ellipses and study the free parameters in order to try to find some correlations between them. We use a galactic model with an axisymmetric background with a bulge, a disk, and a halo. Superimposed, we have a logarithmic spiral potential. In order to find these where it is located, this density wave, we must locate the main resonances of the potential using this figure, where here we plot the angular velocity of the circular orbit of the axisymmetric orbits, the epicyclic frequency, and the combination between the two of them. For example, for a certain pattern speed, let's say, which is the red horizontal line, we find the crosses of this horizontal line with the curves of omega minus kappa over 2, and there we can locate the inner liminal resonances. Here in this model, we see that there are two inner liminal resonances. Then we can locate the fourth one resonance and the corrotation radius. The spiral density wave is located between the inner liminal resonance and the 4-to-1 resonance, because there the orbits become more rectangular and can no longer support the spiral structure. Okay, now we find the periodic orbits with the help of the phase space by using convenient action angle variables, and we see that the X1 periodic orbit, the black one, exists and is stable for small perturbation all through the radius of the galaxy, while there are some other two periodic orbits, X2 and X3, the red one and the blue one, which exists only between the inner and between the first and the second inner liminal resonance, but do not support the spiral structure. So we have some free parameters in our problem, which are the amplitude of the perturbation, the pattern speed of the spiral arms, and the pitch angle of the spirals. And we want to find some correlations between them. We use first the characteristic curves, which is a value of that gives us as the amplitude of the epicyclic oscillation for a particular closed orbit. This is a very important value because it tells us how far from the circular orbit the elliptical orbit is, and the density wave is only in the decreasing part of this value, because when it increases, that means that the orbits are very elliptic, they intersect with each other, and they can no longer form a well-spiral arm. Here we see three cases where we want to find the dependence on the amplitude of the perturbation, where we, in the first case on the left, the perturbation is only 5%, in the middle is 15%, and 30% perturbation on the right. We see that they are well-defined, a well-defined spiral structure for the 5% of the perturbation. And on the phase space, we can see that they are stable. X1 is a stable periodic orbit with no chaos at all. And it makes a good spiral density wave between the inner liminal resonance and the 4-to-1 resonance. The final orbit has a rectangular shape, and from there on, it can no longer support the spiral structure. For the 15% of the perturbation, we can see in the phase space that chaos is introduced after the inner liminal resonance. However, X1 orbit is still stable, and it has a material around it that can support the spiral structure. The spiral structure is more well-defined and more confined, while for the case of the 30% of perturbation, we have chaos is introduced all the way outside the inner liminal resonance and up to the 4-to-1 resonance. There are no more stable periodic orbits, and therefore this is an unrealistic case. And so we have some, so we see that this perturbation is not a realistic one. So we have a plateau of the perturbation up to 15%. Approximately. Here we see the dependence on the pattern speed. if we have a constant amplitude and a constant pitch angle. And we see that for decreasing pattern speed, this wave goes to larger d, and it is more wide for larger d. This is something that has been also observed in real galaxies. We also plot here the X1 families inside the inner liminal resonance, where we see that they intersect with each other, and they don't give a good spiral density wave. And finally, we see the dependence on the pitch angle, where we see that for small pitch angle, chaos is introduced, and therefore we can have no longer a realistic spiral density wave when we have a constant amplitude and a constant pattern speed. So we put all these values in a table here and trying to find some correlations between these three parameters. We have the amplitude, the pattern speed, and we have the pitch angle, below which the X1 family becomes unstable outside the second inner liminal resonance. So the conclusion is that strong spirals have statistically more open spiral arms, something that it has been also observed in real grand design galaxies. Here in this picture of a paper of Grospol in 2002, where we have the amplitude of the perturbation and the pitch angle. So indeed, we see that strong spirals have statistically more open spiral arms. Another conclusion is that spirals that spin faster can be statistically tighter than slower ones. Well, when we go now to the bar spiral galaxies, this theory can no longer explain the spiral arms, because we have no ordered orbits. Here we have a lot of chaos, and it was a great puzzle for many years for the astronomers. What is the building blocks? What are the building blocks in this case? Now, for the first time in 1996, in a self-consistent model of bar spiral galaxies, in a paper by Kaufman and Kontopoulos, they have found a sticky chaotic orbit that stays for a long time at the envelope of the bar and in the inner parts of the spiral arms. And a decade later, almost simultaneously, in two groups have introduced the theory of the manifold theory for chaotic spirals here in our center, at the Center for Astronomy in the Academy of Athens, as well as in Marseille, introduced by Romero Gomez and Harsoula. And they have shown that chaotic manifolds, chaotic orbits can support, in this case, the spiral arms. And by two different versions of this theory, the one called apocentric manifolds, I'm going to explain to you in a while, and the other tube orbits for unstable invariant manifolds. Here we see a very nice picture of the apocentric manifolds. What are the apocentric manifolds? They are the apocenters of the orbits that have initial conditions along the unstable asymptotic curves emanating from the Lagrangian points L1 and L2 at the end of the bar. Later on, Konstantinos Zulumi will explain to you in more details what are these unstable manifolds. We see that in the case where we have only a bar in the potential, we still have some bar-driven spirals, but we also have a ring that is perpendicular to the axis of the bar, and this is something that can be observed in real galaxies. While in the case when we have a spiral potential, there is no ring, but there are spiral arms emanating from the end of the bar. And if we calculate...
2 minutes.
Okay, if we integrate the orbits for a much larger time, we see that they stay there because they have a lot of recurrences back and forth. As a matter of fact, the manifolds are the path on which the chaotic orbits are forced to move before escaping, before getting away from the system. And of course, this is for one pattern speed. That means that the bar and the spirals have the same pattern speed. But in a recent paper of ours, we have also tested the manifold theory in the case for two different pattern speeds, where the bar rotates more faster than the spiral arms. In this case, the manifolds are time dependent, but we see that they can still support the spiral structure. Of course, this is the last transparency. Of course, a very interesting case is when the two theories can coexist. I mean, this is a very nice picture of from Patches 2017, where in a response model of slowly rotating spiral galaxies, we see that there is a spiral inside a spiral. For the inner spiral, we see here that the flow of the orbits, the velocities across the spiral arms. So we understand that here the building blocks are made by precessing ellipses, while the outer spiral, for the outer spiral, we see that the flow of the velocities are parallel to the manifolds, to the spiral arms. So here we understand that there are chaotic orbits that support the outer spiral arms, and this is a nice observational tool for the observers to understand which is the case. And so I leave you with the conclusions, and our future work is finding the analytical relations for the periodic orbits for any given axisymmetric potential in the case of grand design galaxies, and then make comparison with numerical results. Okay, thank you very much.
Great, fantastic. Thank you very much for this nice overview and very nice work. Are there any questions from the audience? Now you're able to unmute yourselves and open your video cameras if you wish. I don't see any raised hands at the moment. Let me see my notes. Right, so have you observed any of these density waves in local galaxies, maybe in our Milky Way, and how difficult it is to observe something like that?
Yes, in our Milky Way, of course, we have semantic representations, but we can have also some figures of spiral arms. And in this case, we're not sure. We suppose that because we have a bar in the center and we have a lot of chaotic motion, we suppose that the theory that explains the spiral arms is the manifold theory out of chaotic orbits. But it can also be the other theory of precessing ellipses, because we see that we have two very well-defined spiral arms. So we don't have yet many data from the Milky Way to be sure that this is the one or the other theory.
And if I may, how local are these density waves, or do they go through the whole galaxy?
Of course, in a galaxy that it is always in a circular evolution, we cannot find static density waves, but there are of course some physical barriers, some inner and outer physical barriers that can reflect these waves, the so-called Q barrier in the inner liberal resonance. So it may grow, and also this can ensure the longevity of these spiral density waves. Of course, they are not static.
Fantastic. Ioannis Miserlis, can you unmute?
Yes, hello, thank you for the nice talk. Sorry, I'm not in this field, so maybe my question is naive. My question is there a one-to-one connection with the winding of the spirals and the rotation of the central part of the galaxy, where we have maybe a black hole and accretion disk, or can be opposite in the sense of rotation?
You mean the winding, yes. The pitch angle? You mean the pitch angle? Because we said that there is not a winding of this. I mean, the pitch angle stays almost constant, but we were able to find correlation with how strong is the spiral perturbation. In the case where there is a bar, as you say, or a black hole in the bar, then this theory is no longer valid. We have to go to the other one, to the manifold theory. So we cannot find such a correlation where chaotic orbits then support the structure, but they stay there for very long times because they have many recurrences, so they can support this structure even for a Hubble time, for example, because they pass them much longer time before getting away from the system.